So let's consider a container of fluid. And in this case, let's just make it liquid for the sake of simplicity. So this container has an area or a bottom surface with some area A, and it is at a height H. And this is going to, be filled with a liquid. The liquid's supposed to go up all the way to the top. You have height H here. Let's ask ourselves, what is the force of gravity being exerted on this thing? In other words, if I were to draw a free body diagram, I would have this, and I would have some sort of force exerted upwards by the bottom of the container here. But what I'm curious about is, what is the force of gravity acting on this liquid? Okay, well, we know that the force of gravity is mg, right? You might be like, well, what are you talking about? It's sitting right there. Well, I've got mg, sure, no problem. But what about the mass of this liquid? Well, just humor me for a second. Let's recall my definition of density as mass per unit volume, which I can then solve for the mass of a specific sample of this thing by just forming rho times the volume. So I've got whatever volume this is, we'll figure that out in a second. If I know the density of this, I can talk about the mass of this fluid, this liquid, as rho v. And so let me rewrite my gravitational force as rho v g. Get used to seeing stuff like this, and whenever you see rho v, you should get to the point where your mind just reads that as a mass. This is absolutely a mass, and we're going to use this to find some other interesting things, but that's a mass, right? Just by rearranging the definition of density, rho times a volume gets you units of kilograms. It is a mass. All right, let me rewrite this without the box, rho vg. Okay, well, I'm given some physical dimensions of this thing. Maybe I can rewrite the volume in a way that makes some more sense. I've got the area of the bottom. I've got the height of the side. This dimension times these two dimensions, right? Remember, area is a two-dimensional quantity. Gets me the volume of this. The area of the bottom times the height gets me the volume of this. So I can write this now as rho a h g. Fair enough. Now, let me ask you this question. What is the pressure being exerted on the bottom of the container? Well, we know the force has got to equal mg, right? How do I know that? Because this liquid is in equilibrium. And this Newton's second law says that the force upward has got to balance the force downward. So this force is what's being exerted upwards from the bottom of the container. Newton's second law and the fact that this is in equilibrium tells us that that force is equal to mg. Okay, well, what if, and I've already written mg as this. Now, what if I want to know the pressure? Well, remember the definition of pressure, force per unit area. If I have determined that my force is this, I just need to divide that by the area of this bottom surface to determine the pressure. Rho A hg over A, and notice that's the same A. It's the area of the bottom surface. That's what's providing the upward force, and that's what I use to determine my volume. And so that goes away, and I get rho, I'm going to switch order here, rho GH. And if that's starting to sound somewhat familiar to you, let me rewrite this now in terms of what the density actually is. mgh over V, where m over v is the density. That's interesting. This is energy per unit volume. I'll tell you right now, this is how physicists typically think about pressure. Is there anything wrong with thinking about it as force per unit area? Absolutely not. Are you going to have to think about this to solve certain problems? Absolutely you are, but you should also get in the habit of looking at it as some sort of energy per unit volume. That's actually a really interesting way to look at it, and it will make problems later when we start doing things like Bernoulli's equation and some fluid dynamics make a lot more sense. If you need a force, of course, it's right here, but if you need energy, you can think about this. And we're going to see a form of this that's not just gravitational potential energy like MGH is. There's a kinetic version of this as well. But energy per unit volume is a really good way to start thinking about pressure. All right, so where are we? Well, the rest of the thing I want you to see, I'm going to go back a step and write it as this. Pressure is equal to rho GH. Now, what can I do with this? Well, this is, as we've derived it, the pressure at the bottom of this container, right? Okay, fair enough. What if I were to arbitrarily construct a surface here? And I would say, okay, well then what's now the pressure at this depth? I could do the same thing. I could figure out what force is being put up from that surface divided by the area. But you see, for that, I will have a different H. And what would we expect to find? Well, if we compare our two H's, in the first case, H was large, and the second case, H is small, but if you run through the math, you'll see that you actually get the same expression, but with different H's. What that means is that the bigger H is, the larger the pressure. The smaller H is, the smaller the pressure. Okay, let's remove this arbitrary surface and just talk about now the fact that we can determine the pressure at a certain depth in a fluid if we know how far down from the surface of that fluid we are. Now, if you've ever swum down to the bottom of the deep end and felt your ears dying to pop, that's probably not much of a surprise. The pressure in a fluid varies with depth. Let me go to a different sheet and say that and write that down explicitly. Pressure in a fluid varies with depth. Later on, when we talk about Archimedes' principle, we'll start to investigate why that's the case. Spoiler alert, it has to do with gravity. But pressure in a fluid varies with depth. So now when I write this, rho GH, what I have to define now is H is the depth in the fluid. So we're used to measuring H up. For this application, we've got to measure H down. So just one little twist to what we've been doing. But H is now the depth in the fluid, the distance I am away from the surface. Think about it. If H is 0, if you're measuring down, that means you're at the top of the fluid and there's no pressure there, right? That doesn't even make any sense. So rho GH is now the depth in the fluid. Okay, so what happens when I have two fluids? So let's say that I have some water and some air. So here's air and here's water. And we've already seen, my previous example was based upon a liquid here, that, you know, if this is some H, the pressure at that depth is equal to rho GH. Okay, well, what about in the air? Will this work for the air too? And the answer is it absolutely will. Air pressure is a thing, and if you go all the way up to the top of the atmosphere, H for that case is 0, but if you come down, you start to develop some air pressure. To the extent that when you get down here to what we call sea level, you have reached a certain air pressure. Now, you're gonna have to just kind of go with me on this one. The actual pressure anywhere at sea level kind of varies back and forth. It actually depends on a lot of factors. It depends on the humidity of the air. It depends upon the temperature. It depends on other things. But we have settled on a standard air pressure at sea level, which we usually call P naught, or atmospheric pressure. The atmospheric pressure, like I said, it's a number. Whether or not the actual pressure at sea level is that exact number, it depends upon atmospheric conditions. But at the very least, this is a really good average value, kind of like 98.6 degrees Fahrenheit. It's a really good average value for what pressure at sea level is. Now, so this is a constant is what I'm saying. Now, what does that do here? Well, as we derived this expression, we derived it only for this fluid. But this fluid has to come into play as well, right? The top of the ocean here is already under some pressure from the atmosphere. So now what I have to do is amend this equation and say that the pressure at some depth h in a body of water or some other liquid is going to be equal to the atmospheric pressure, what I have here at the surface, plus rho GH, where rho is the density of this fluid, or this liquid, I should say. It could be a fluid. And H is the depth in that fluid. We've already taken care of that calculation here in the air. So if you are in some sort of fluid that is exposed to the atmosphere, and that's a really big consideration. Maybe I should have stressed that a while ago. If this fluid is exposed to the air, this is the expression we're going to need to use. We're going to have to take into account the variation of pressure with depth in the fluid plus the atmospheric pressure at the outside. If this is not open to the atmosphere, you don't have to worry about this. You just have rho GH. But if it is open to the atmosphere, you have this additional factor. Air pressure, standard air pressure, you should say. Atmospheric pressure, you can say. We'll see what this is as far as a numerical value when we do some examples. I'm not actually worried about what value it is. I'm worried about that you understand this expression and where it comes from.